Welcome. This is Professor Nathan Weezy of Marquette University. This section we're going to talk about the lead lag controller in the digital control of power electronics. All right, so what is a lead lag controller? Typically a structure looks like this. Essentially when you look at it, what you have is you have a zero that you can put wherever you want by controlling omega z. You have a pole which you can put wherever you want, which you can control by setting omega p. And then also you have an integrator, and generally the integrator is there for ensuring zero steady state error. So this is a traditional structure for a lead lag controller. Now, before I move on, you can actually have a second order one, or essentially, it depends on your plant. If you have a lot of poles and zeros, you might have, for instance, in this example, two zeros at the same spot, that would be the squared part, and two poles again at the same spot, that is the squared part. So this is also a lead lag controller. It's just a higher order one in case you need to deal with a plant that has more poles and zeros. Okay, so let's go back to the original one here. We have one pole, one zero, and an integrator. And essentially what we have are three things we're trying to solve for when we design this controller. It's omega z, omega p, and k. That's what we're trying to find in the design of this. Now, what I'm going to talk about next is a design process for selecting omega z, omega p, and k. You don't have to do this. You could place them arbitrarily by yourself. You don't have to follow this method, but this is a good method that works for a lot of different power electronic topologies and control. All right, so let's take a look first at what's happening here. You see I have a Bode plot here. I actually have a Bode plot for, it looks like 1, 2, 3, 4, 5, 6 different controllers. And the only difference between these 6 controllers are where I placed omega z and omega p. I've actually kept k constant here. And what I'm actually doing is separating these poles further and further apart. Okay, so for instance, this really light blue line down here, that's where the pole and the zero are really close together. For instance, what if they were here and here? Excuse me, I have that backwards. What if I had the zero here and the pole here? They're really close to each other in frequency. Yeah, we'd start to go up a little bit, but then we go down right away. This is in phase, and of course the gain will come down, come up a little, and go right back down. Now you can see the shape of the phase plot here. But let's say I separate them a little bit more. For instance, this green one, let's put the zero, let's say approximately over here, and the pole over here. Okay, so we're going to get a little more phase out of here, and you can see the light green one comes and levels off for a little bit and goes down. And generally what I'm trying to show you here is there's a trend. As I pull these poles, the pole and zero further apart, I get a larger phase bump, and I get a flattening of the gain for some region, right? Let's go up even to this this red one. Here it goes all the way up, flattens off at 0 degrees for phase and back down to minus 90. Here in the red gain plot, you see a nice flat area and down. So the reason I'm showing this to you is because in this design process, we're actually going to exploit this phase relationship here. So everything's done with a center frequency of, in this case, 100 hertz. That means everything is centered around here in terms of the phase. Now this is interesting because what I can do with this type of design process by centering the pole and zero between a particular frequency is I can set how much phase boost I want. For instance, if I pick this controller in green, I would get this much phase boost at 100 hertz. Or if I picked, let's say, the controller, the purple one, I would get this much phase boost from this controller at that frequency. And so what we're actually going to do is place the pole and zero at the proper location so we get the desired amount of phase boost at a particular frequency. And what this is going to do is push our phase back up so we don't go past minus 180 degrees before the gain hits through 1. And that ensures us stability, okay? So we'll do a couple examples to kind of work this out and see what it means. But in this design process, all we're doing is putting the pole and zero, we're putting them closer together or further apart depending on how much phase boost we want. Okay, so the equations that do this are outlined in equation 2 through 7. So when you have a control system that you are trying to design for, you could determine how much phi boost you need by this equation. Let me work through this. What is what? So first, the first term is minus 90 degrees. Well, the minus 90 degrees comes from the integrator. You're always going to start off at minus 90. You can also see that in the phase plots. Everything starts over here at minus 90 at low frequency. So you always have that. And then, depending on how much phi boost you want, you have this phase margin term here. This is, you get to set at design time, and I'm gonna sweep some of these so that you can see what phase margin effect has. And then lastly, this term here, this is the phase of the plant at your interested frequency. So what this will do is you'll get an equation for how much phi boost you need from your controller in order to set the desired phase margin. So you're going to, for example, if I want 60 degrees of phase margin, I'll pick 60. I solve this simple equation too, and I'll get how much phi boost I need at that frequency to get that phase margin. Okay, great. The next thing you'll get is K boost. This is a factor. This looks like a completely arbitrary equation, but what this sets is how far apart the pole and zero are from the crossover frequency. So FC is going to be our bandwidth or crossover frequency. This sets the ratio between those two because the pole and zero are basically going to be centered at FC. And how much are they centered by? It's this ratio. Okay? All right. So equation 4 here. This essentially is how much gain do I need from my controller in order to push the open loop transfer function to pass through a gain of 1 at the desired crossover frequency. So how much gain needed from controller? All right, now once you have those three terms, you have phi boost, K boost, and how much gain you need from the controller, you can calculate the location of the zero, pole, and the gain of the controller with equations 5, 6, and 7. So this right here, that's the controller 0. This is the controller pole. And this is controller gain. Okay, now once you have that calculated, you have a complete controller design. Let's walk through an example and see how this works. All right. Well, actually, let's talk about this one quick before we do an example. So essentially what we have here is we have almost the same structure, except for now we have a double pole and a double zero. Okay, it's almost exactly the same. So we have a double zero, double pole. Okay, it's the same strategy here with this design. You would use this for a higher order plant. What happens with this one again is, here's my center frequency, FC. As I pull the poles apart, I get more phase boost. As I have them closer together, I get less phase boost, as you can see through these varying phase plots. And then you can also see with the gain, since I have a double pole plot, I'm going to start down at minus 20 dB per decade due to the integrator. Once I hit, guess what, the double zero, I start going back up at 20 dB per decade. And then once I hit my double pole again, I'm going back down at 20 dB per decade. So you never really have kind of a flat level like you did with the single pole and zero variant. Now you could do the same thing, the same design process, depends on how much phi boost, how much phase margin you want. So you could set the phase margin that you would like. You get to set FC, which is the bandwidth, and then you can calculate these values. So phi boost will be how much boost you need, how much phase boost you need at that particular frequency. This is a ratio of omega z to omega p centered around FC. So it's a ratio of omega Z and omega P centered around FC. This is the gain needed from controller. Same thing. And once you calculate these three, you can, equations 12 through 14 will give you the zero, pull, and gain of the controller. So this is the zero, this is the pull, and this is the controller gain. Okay, now the major thing I want to point out is the only difference between this set of equations and the previous is right here in K boost. You have this factor of 4 instead of 2, and that's just due to the doubling of the poles and zeros in this. Other than that, the design process is exactly the same. All right, let's do an example with a single pole and a single zero. Let's assume that we have this plant right here. Okay, we have 1 0 up top, and we have 1 pole. All right, if we do the Bode plot, you can see before we hit the 0, we have a nice flat gain of 40 dB. We hit right here, this would be our pole. We start going down at minus 20 dB per decade. And then we hit our 0. And we level back off. Okay, that's the gain plot. And the same goes with the phase here. Okay, what I'd like to do is design controller for a crossover of 1 kilohertz and a phase margin of 60 degrees. Okay, so this is our plant transfer function. So what you want to do is calculate the gain and phase of the plant at those frequencies first. So if we look at this here, this is right here. This is the gain of the transfer function, GPS at FC. And in this case, it's about 20 dB, just by looking by inspection. And then, of course, here, this is our phase of GPS at FC, the desired bandwidth. Okay? So we know what those are. There are certain numbers. Let's approximate this to be, what, minus 78. Okay, cool. Now what we're going to do is try to design a controller that will give us a crossover frequency of 1 kilohertz and a phase margin of about 60 degrees. So you can follow those equations up at the top. And if you do that, these are what you get for your controller gains. Okay, and looking at these numbers, they're pretty meaningless, but let's take a look at the actual controller on the Bode plot to see if it makes sense. All right, so if you plug these numbers into the controller, this is what you get, and that is our lead lag controller. Now let's plot the lead lag on a Bode plot and see if this makes sense. All right, first, remember I have this up here. Blue is the plant, so that's GPS, aka the plant. In red, we have the controller. And let's check something out. If we added these two together, remember this is in dB, so if we multiply them, you add in dB. If we multiply their gain unitless, we would add. So check this out. At FC, remember this is FC. FC is 1 kilohertz. If we add, what do we get? Well, we have 20 dB from the power stage, and guess what? From the controller, we have minus 20 dB. So the net result would be 0 dB, which in gain is 1, which means we crossed over the frequency at the crossover frequency. In other words, we're verifying a controller design. We have the proper controller design for pushing the open loop transfer function to cross through a gain of 1 at FC, or 1 kilohertz. Let's also check our phase margin. So if we're multiplying the phases here, we can simply add these. Let's see what we have. So from the controller, well, let's call this approximately minus 40 degrees. And then this was minus 78 something degrees. So if we add these together, what do we have? We have about approximately minus 120 degrees, which means our phase margin was 60 degrees, which is what we designed for. So that is a check. Remember, phase margin is how far you are away from minus 180 degrees. Okay? All right, so our phase margin spec is checked. That's great. Now let's take a look at the open loop transfer function, which I've plotted here in yellow. So you can see that at FC equals 1 kilohertz, what do you note? You note that I cross through the gain for the yellow guy right at 1 kilohertz. Okay, and also we can check the open loop transfer function. What's that look like for phase here? You can see we're right about minus 120 degrees. Okay, that's awesome. All right, so the last thing we're going to check is our closed loop response. That's actually plotted here in purple. We have a gain of 0 dB, which is a gain of 1 from 0 frequency up to 1 kilohertz, and then we roll off like a low-pass filter, which is great. That's exactly what we want. It means we'll respond to any reference command between 0 and 1 kilohertz and be able to track. Outside of that, we won't be able to track, or it's a low-pass filter on that. Okay, now let's take a look at this in the digital domain. We have converted this controller from the continuous time S domain to the digital domain using the Tussin approx. So let's put this here. This is Tussin approximation. And let's take a look at a step response. You can see we go up pretty fast and we settle down nicely. I have plotted both the continuous time response and the digital time response. One thing you can note here is that this 1 is times 10 to the minus 3, so that's about 1 millisecond. And if you look at this, we're responding and settling in about 1 millisecond, or 1 over 1 kilohertz, which is essentially the bandwidth. So the bandwidth has a strong correlation to how long it takes you to actuate and settle at a response. So in other words, we designed for a bandwidth or a crossover frequency of 1 kilohertz. That means we ought to expect our system to respond to a command by about a millisecond, approximately. It's a loose correlation. Okay, so the other thing that I've done here is, remember, this was done for a phase margin of 60 degrees and FC was 1 kilohertz. That's this plot. Now what I've gone ahead and done is swept a couple different phase margins so you can get a little understanding of what phase margin does. Here I've swept phase margin from 20 degrees all the way to 90 degrees in steps of 10 degrees. And what you see here is 20 degrees means that your open loop transfer function is at about minus 160 degrees at the crossover frequency. So it means we're pretty close to instability. So you can see that our response is very ringing, right? It rings quite a bit and it takes a while to die out. Now, as we increase the phase margin, you can notice that we're getting essentially more and more damping. So we're getting less ringing. And then kind of the design that we had was the green one, which was about 60 degrees here. That one has a pretty decent response. It overshoots by a little bit, but it settles back in. But we might be better served if we went with, for instance, 80 degrees or 90 degrees. It's a pretty good response. Comes up a little and locks down. 90 degrees is really good. Looks kind of like a perfectly damped system. So this kind of gives you a little bit of understanding how phase margin correlates to the type of response you get. And you notice that essentially these times here that it takes, this rise time, is really unchanged. It is unchanged with phase margin. So there's no real correlation with this rise time to the phase margin. It has everything to do with how much damping you have. Now the other thing I'm going to show you is we didn't do kind of a closed loop pole plot or a plot of the poles and track them where they go type of design. We did it from the Bode plot, but let's take a look at what phase margin did with the closed loop system poles as we change them. So what we're looking at is a pole zero map as I swept across the various phase margins, and you saw the step response first, but let's take a look at our phase margin of about 20 degrees. That would be this one. If you look over here, here are two of my poles and I have another one here, which is really interesting because this line out here and this line here is a damping of about 0.17. So that's not a lot of damping, which is why it rings quite a bit. And as we increase phase margin, what you're seeing is the poles are moving to higher damping ratios, which is good. It means we have less ringing. And of course, when we hit about 80 to 90, wait, let's see, hold on. About 60 degrees of phase margin, we're pretty close to the x-axis, which means we're not going to have much ringing at all. And then you can see that the poles move to the left-hand side on the x-axis. It means we have really good damping. Okay, so you can see how this phase margin affects or how it correlates to the system poles. This concludes the control design for a lead lag controller. Thank you.